So, of course, one of the most famous examples of simple oscillations is that of a simple pendulum. So this video is about how to think about simple pendulums from the perspective of mass spring oscillators. Okay, so let's draw a simple pendulum. Here we have the ceiling, we have, this is the vertical, and then the pendulum itself. So let's say this is length L, mass M. Okay, and then of course gravity G. And you can derive the equations that govern the simple pendulum. I'm not actually going to do this right now. I'm just going to write the equations of motion directly. You would use techniques from homework 4 to derive equations of motion for this. But in any case, let me just write down the equations of motion. So the equation of motion, once you write it out, is actually, it's going to be ml square alpha equals m minus mgl sine theta. Okay, where alpha equals angular acceleration, if this is theta, this is alpha is theta double dot. Okay, it's the angular acceleration. So you can use concepts from homework 4 or homework 8 to derive this equations of motion. Maybe at the end of this video I might actually derive this equation. So but let's just say we are given this equation. Let me call that equation 1, and then let's sort of rearrange it slightly. Ml square theta double dot plus mgl sine theta equal to 0. We can simplify this if we want, so we can divide through by ml square, and we get theta double dot plus mgl divided by ml square sine theta equal to 0, or theta double dot plus g over, looks like I'm using a different L, but doesn't matter. Okay, g over L sine theta equal to 0. Okay, this is sort of one of the most famous equations, differential equations in mechanics. It's the equation governing the motion of a simple pendulum. Okay, it's similar to mx double dot plus kx equals 0, but then instead of, so x is analogous to theta, but instead of x we have sine theta here. Here we have x double dot, here we have theta double dot, but instead of x we have sine theta. So what we can do is use a small angle approximation. Or a linearization. Which is to say, for small theta, we have sine theta approximately equal to theta, or the Taylor series of sine theta about theta has theta about theta equal to 0 has theta as the first term. Okay, so we say, so replace sine theta with theta, which is an approximation, of course, right? An approximation that is only true for small angles theta. So we get theta double dot plus g over L, theta equal to 0. Okay, so this is the linearized equation. It's linearized because sine theta is a nonlinear function, and we've taken that and replaced it with theta, which is of course a linear function of theta. Okay, so this is called a linearized equation or a linearized differential equation. And now this one is completely analogous to mx double dot plus kx equal to 0, where instead of m we have the number 1, instead of k we have the number g over L sine theta, right? So in fact, if we can sort of more analogously write this as x double dot plus k over m x equal to 0. So let's just write that here. Analogous to, exact correspondence with, mx double dot plus kx equal to 0, or x double dot plus k over m x equal to 0. So what this means is that for this equation, so let's call this equation 2. For equation 2, this is equation 2. Let's call this equation number 3. For equation 3, omega n is sort of analogous to k over m. You just go square root of g over L. Okay, that's it. And then time period, you can go fn equals omega n by 2 pi, or tn equals 2 pi by omega n, etc. But this is the key relationship that we get for simple pendulum, where the frequency or the angular frequency is dependent on the length of the pendulum and the gravitational constant. It's inversely proportional to the square root of the length of the pendulum, where if you make the length shorter, the frequency increases. Shorter pendula oscillate faster. And more importantly, it is independent of the mass of the pendulum, because the mass sort of gets cancelled. So that's it. So that's how for other systems, like for instance a simple pendulum, you can essentially use all the things that we derive for this equation by making essentially correspondences with, it's the exact same equation except with the constants replaced and the variables replaced or renamed. So the exact same derivations apply, so you can just use the same formulas as before. You can sort of think of this as a stiffness and this as a mass, or actually in this case this is a rotational stiffness and this as a rotational inertia. In any case, you can make these correspondences with the coefficients here and here, here and here, and you get these formulas. That's it. So there's lots of ways of deriving an equation of motion like this for a simple pendulum. We're just going to use quickly principles from the earlier part of the course, basically particle mechanics. So if you take the simple pendulum, we can draw a free body diagram. There's mass mg acting downwards, tension T acting toward the pivot, and we can decompose the mass mg into, well, if this is theta, this is also theta. So there's going to be mg cosine theta acting along this direction, and mg sine theta acting along this direction. And so that's it for the free body diagram. And then we have the point O out here, let's say. And then let's consider writing an expression. Basically, we want to write F equals ma, right? Let's write an expression for the acceleration of this point. So if you have theta like so, and this is length L, we can define ER and E theta like so, and then write an expression in terms of polar coordinates. If you recall, A acceleration of the point P is going to be equal to, this is motion in a circle, so it's got a special formula. It's minus L or R, doesn't matter. Let's call it R for now, and then we'll replace it with L. R square, so it's a centripetal acceleration, R theta dot square, ER, plus R theta double dot, E theta. Okay, so those are the two acceleration terms. And then you just go sum of forces equals M acceleration. And then in the E theta direction, the only force is mg sine theta. It's actually mg sine theta is in the negative E theta direction. So we go negative mg sine theta equals, and then we go M acceleration in the E theta direction, which is R theta double dot. So that's it, which is ml theta double dot, and ml theta double dot equal minus or plus mg sine theta equal to 0, or if you divide through by ml, you get theta double dot plus g over l sine theta equal to 0. So that's how you derive, at least one way to derive the equations of motion for a simple pendulum. So, sort of another way of deriving equations of motion is to imagine this point mass to be a rigid body, but a rigid body with moment of inertia equal to 0, and then take moments about point O using the parallel axis theorem, and then you will get exactly ml square alpha equals mgl sine theta minus mgl sine theta, where minus mgl sine theta is the moment about point O, and ml square is the moment of inertia of the point mass about point O alpha. So I alpha equals moment. So that's another way of deriving the same equation.